The Geological History of Britain, A Journey in Space and Time. This film is based on a presentation given to the High Wycombe and District U3A Geological Group in September 2023. The script is by Martin Utica, with revision and additional material by Phil Platt. Video production by Phil Platt, January 2026. Since both Martin and Phil are no good at narrating, Phil tends to mumble and Martin rambles on and on. We have given the job to our AI assistant, Rachel. We think she's pretty good at it, and hope you do too. This is a simplified geological map of the British Isles. It looks very colourful, but it's also quite complex, isn't it? You may be asking yourself, what do all these different colours mean? Well, today you're going to find out. For starters, did you know that the UK is one of the most geologically diverse countries in the world? You can see from the key below the map that rocks of every geological period and every main rock type, sedimentary, igneous and metamorphic, can be found within the British Isles. It's not a continuous record, there are some gaps, but every period is represented. Not many countries can claim that. Also, many of the geological periods, which are now used worldwide, were named by British geologists in the 1800s, and many refer to locations in Britain. For example, the Cambrian, Ordovician and Silurian periods were named after Welsh tribes because that's where they were first mapped, and the Devonian was first described in Devon. Some of these names may be familiar to you, such as the Jurassic from the movie Jurassic Park, but others, probably less so. Don't worry, you'll soon get familiar with them. In general, the oldest rocks are found in the northwest of Scotland, and they get progressively younger towards the southeast. So let's take a journey together, from soon after the formation of the Earth, right up to the present day, to see how Britain has been put together, bit by bit, over the course of the last 3 billion years. But before we start, let's do a quick recap of the geological timescale. Don't worry too much about all the names. I will explain. This timescale provides us with a framework in which to place geological events. It's a bit like the periodic table is to chemistry, or the way we divide historical time into the classical era, Roman times, the Dark Ages, Middle Ages, etc. Earth formed 4.56 billion years ago. This enormous time span is divided into 4 eons. The Hadean Eon, which means hellish, the Archean Eon, meaning ancient, and the Proterozoic Eon, meaning early or proto-life. Together, the first 3 eons are known as the Precambrian Super-Aeon, and this represents 88% of Earth history. And finally, the Phanerozoic Eon, meaning visible life, has lasted for the last 541 million years. This is where the first clear fossils appear in the rock record. This last eon, which represents only 12% of the age of the Earth, accounts for most of the geology of Britain. The Phanerozoic Eon is divided into 3 eras. The Paleozoic, between 541 and 252 million years ago, and means old life. The Mesozoic, between 252 and 66 million years ago, and means middle life. And the Cenozoic, the current era, which started 66 million years ago, means recent life. These 3 eras are further subdivided into 12 periods, which we will cover during this video. To try and illustrate this, imagine my arm represents all of Earth history. Then the Precambrian runs from my neck to the end of my palm, my shoulder is the Hadean, my upper arm the Archean, and the Proterozoic runs from my elbow to the end of my palm. My fingers represent the Phanerozoic Eon, with each finger bone being 1 era, the Paleozoic, Mesozoic, and Cenozoic. The last period, the Quaternary, started only 2.6 million years ago. This is the time of the last ice age and is represented by the white of my fingernail. The entire history of Homo sapiens would be erased by one stroke of a nail file. Now, let's add a few key events to this timescale. The oldest rocks found in Britain date from the Mesoarchean era of the Archean Eon, about 3 billion years ago. the Caledonian orogeny, about 420 million years ago, of which remnants can still be seen in North America, Greenland, Northern Ireland, Scotland, and Scandinavia. The Variscan orogeny occurred during the late Paleozoic era, and although long since eroded, remains of these mountains still shape much of Europe's upland geology today, especially in France, Germany, Spain, the Czech Republic, and even as far as parts of North Africa. The most recent orogeny, the Alpine, formed mountain ranges still very much in evidence today. The Alps, Pyrenees, Carpathians, and Caucasus Mountains, and not forgetting the Himalayas. Right, now let's start our journey through time. To keep things logical and easily digestible, I've divided it up into 5 sections. The Precambrian, Super-Eon, and each of the 3 eras, with the Paleozoic divided into 2 parts, the older Lower Paleozoic and the younger Upper Paleozoic. In each section, I'll describe the geological periods that make up that eon or era, showing you where rocks of that age are found in Britain. I'll also highlight some of the key events that happened during that time. In addition, I'll show you what rocks were formed and some typical British landscapes from that geological period. Some of it is aerial footage from drones, so I hope you've got a head for heights. I'll also give you some idea of what planet Earth looked like in terms of plate tectonics and the position of the continents, and what was to become Britain. The Precambrian, 4.56 to 0.54 billion years ago. So, let's begin our geological history of the British Isles, starting with the Precambrian. The oldest rocks in Britain are in the northwest of Scotland. Here in the Hebrides, there are very ancient crystalline rocks, known as Lewisian gneiss. Thought to be some 3 billion years old, these rocks are extremely hard and reveal a tortured history during which they have been squashed and heated in several mountain building episodes known as orogenies. Let's not forget, though, that the Lewisian gneiss is a metamorphic rock, meaning it is formed from rocks even older. But we have no way of knowing what or how old these were, so we aren't going there. 2 billion years later, during the Neo-Proterozoic eon between 1,000 and 800 million years ago, huge rivers flowed across this landscape, eroding these ancient mountains and depositing layers of red sandstone, muds, and pebbly conglomerates known as the Torridonian sandstone. Much of the rest of the Scottish Highlands, Shetlands, and Northwest Island are composed of heavily deformed metamorphic and igneous rocks formed during the late Proterozoic and early Paleozoic. Originally deposited as marine sediments and volcanic rocks, they were deformed, faulted, and metamorphosed by continental collisions during the formation of the Rodinia supercontinent 1,200 to 1,000 million years ago, and again during the Caledonian orogeny 425 to 400 million years ago. More about that later. There is also evidence, in the form of unsorted glacial tillites, of a major late Precambrian glaciation 700 to 670 million years ago, sometimes called Snowball Earth. In England, Wales, and Southern Ireland, there are only a few small isolated outcrops of Precambrian age, including the Longmynd in Shropshire, the Malvern Hills in Worcestershire, and Charnwood Forest in Leicestershire. These rocks hint at a very different mode of formation. They are thought to have been created as volcanic island arcs on the edge of Gondwanaland, similar to today's Pacific Ring of Fire. There was no visible sign of life in any oceans or on land, just barren rocks. Precambrian rocks and landscapes. This is a typical barren landscape found in the Outer Hebrides, worn down by millions of years of erosion, and then again during the Pleistocene Ice Age, between 2 million and 12,000 years ago. The Torridonian Mountains consist of mainly red and brown sandstones, arkoses and shales, with coarse conglomerates at the base, deposited as giant alluvial fans. Some of these rocks were derived from the erosion of the underlying Lewisian gneiss, but the bulk of the material was obtained from Rhodinian mountain chains that have been completely worn away. Some of the most dramatic mountains in the Northwest Highlands, such as Sylvan, are composed of very hard, gritty, horizontally bedded Torridonian sandstone sitting unconformably on the Lewisian gneiss. One of the few locations in England where Precambrian rocks are exposed is the Charnwood Forest in Leicestershire. Here, pyroclastic rocks were erupted from ancient volcanoes which were metamorphosed over time, and within which may be found markfieldite, a rock unique to the area. Also, sandstones and siltstones were deposited in a shallow sea, and it was in these that one of the oldest known complex, multicellular animal fossils, Charnia masoni, was discovered in 1957. So now we come into the Paleozoic era. I have divided this into two parts, the Lower and the Upper Paleozoic. The Lower Paleozoic era is made up of three geological periods. The Cambrian period, 541 to 485 million years ago. The Ordovician, 485 to 443 million years ago. The Silurian, 443 to 419 million years ago. Rocks of this age are found in a thin band in the northwest and the southern uplands of Scotland, the Lake District, North and Mid Wales, the Isle of Man, several parts of Ireland, and a few small outcrops in England, for example Charnwood Forest, Nuneaton and the Wrekin. The Cambrian, 541 to 485 million years ago. It was during this period that most major groups of animals first appeared in the fossil record, over a relatively short span of time, known as the Cambrian explosion. During this event, life diversified rapidly, producing creatures with hard shells, complex eyes, and new body plans that still shape animal life today. It is thought that a mix of rising oxygen levels, genetic innovations, and ecological interactions helped trigger this burst of evolutionary creativity. So, what did the world look like during the Cambrian period? This is a rather unusual view of Earth's southern hemisphere, looking down on the South Pole. But the layout of the continents was very different then, and the British Isles were split into two parts at this time. England, Wales and Southern Ireland were attached to Europe, which was at that time part of the Gondwana supercontinent along with South America, Africa, Arabia, India, Australia and Antarctica. It was located at latitude 60 degrees south, quite close to the South Pole. Scotland and Northern Ireland were attached to the continent of Laurentia, which consisted of North America and Greenland, and was located 20 degrees south of the equator. The two continents were separated by the Iapetus Ocean, which at the time was some 4,500 kilometers wide. There was a mid-ocean ridge like in the Atlantic today, and the two continents were originally moving apart. How, you may ask, do we know the latitude of these former continents? Well, some very clever Earth scientists realized that we could use the Earth's magnetic field to work this out. Here is a diagram of the Earth's magnetic field. Now look at the lines of force. Notice that at the equator the lines of force are parallel to the Earth's surface, whilst at the north and south poles they are vertical. This is called magnetic inclination. When molten lava cools and solidifies, any minerals containing iron align to the dip of the local magnetic field. So by taking lots of samples of ancient lavas of a particular age and measuring their paleomagnetic dip, it is possible to work out the paleolatitude at the time they were formed. Cambrian rocks and landscapes. The Llanberis Pass in Wales is famous for slate. This is composed of Cambrian mudstones, which were subject to contact metamorphism during the Caledonian orogeny. Its property of being able to be split into thin sheets, together with its hardness and impermeability, made it an ideal roofing material, and was extensively quarried and exported worldwide during the 19th and early 20th centuries. Deep water sandstones, known as greywacke, often formed as a result of submarine avalanches called turbidites. This is the case in the rocks of the Chrynog Mountains in Wales, which form the core of a major uplifted area called the Harlech Dome. The Harlech Dome, which extends from Barmouth in the north to Cadair Idris in the south, comprises about 2,000 meters thickness of sandstone, mudstones, siltstones and greywax laid down in the marine Welsh Basin during the early to mid-Cambrian period, collectively known as the Harlech Grits. The Ordovician, 485 to 443 million years ago. During the early part of the Ordovician, rifting occurred in Gondwana, causing the landmass containing England, Wales and Southern Ireland, known as Avalonia, to split away from Gondwana, forming the Rheic Ocean. Meanwhile, the forces of plate tectonics caused the Iapetus Ocean to shrink. As the ocean floor was subducted, it melted, and the magma slowly rose up through the crust to form volcanoes in North Wales and the Lake District. This kind of magma can be very viscous, causing explosive eruptions, like that of Mount St. Helens in 1980. The evidence for this is preserved in the mountains of the Lake District, the Borrowdale volcanics. Ash from these explosions was deposited in the surrounding seas, and later metamorphosed, forming the Cumbrian green slate. There was still no sign of any life on land. The continents were a barren expanse of rock, not even any soil. However, in the oceans there was a continued diversification of marine fauna, with more than 4 times the number of new species than were found in the Cambrian. So this might have been partly due to the very high sea levels, which would have created lots of different ecological niches, from shallow shelf seas to the deeper ocean trenches. Nevertheless, the Ordovician period ended with a mass extinction that wiped out 57% of genera and 88% of species. It is thought to have been caused partly by a major glaciation event, as Gondwana moved over the South Pole, causing a drop in sea level and loss of habitat, and partly because of a reduction of marine oxygen levels. The joining of Britain, the Caledonian orogeny. So let's have a quick look at the plate tectonics which were going on during the Ordovician period and led to the eventual joining of the 2 halves of Britain. At the beginning of the Ordovician, rifts developed in northern Gondwana, similar to the East African Rift Valley today. Eventually, a small continent called Avalonia split off and started drifting north. This microcontinent contained southern Britain, England, Wales and Southern Ireland, part of northern Europe, Normandy, Belgium, the Netherlands and northern Germany, and the eastern seaboard of the USA and Canada, from Rhode Island to Newfoundland. The Iapetus oceanic plate was subducted underneath Laurentia, where it melted and erupted, and a volcanic arc of islands, similar to Japan and Taiwan today, was formed. As the Rheic Ocean widened, the Iapetus Ocean shrank. As oceanic crust was subducted under Avalonia, volcanic eruptions occurred there, creating the North Wales and Lake District volcanics. When Avalonia drew ever closer to Laurentia, it first merged with another small continent known as Baltica, which contained most of Scandinavia. Sediments in the shrinking Iapetus Ocean were now piling up against Laurentia in what is known as an accretionary prism, forming the Grampian Mountains, similar to the formation of the Himalayas. And thus England and Southern Ireland were welded to Scotland and Northern Ireland to form what was to become, millions of years later, the British Isles. Ordovician rocks and landscapes. Some of the highest peaks in Britain were formed by the Ordovician volcanic events. These include Mount Snowdon in North Wales, Helvellyn with its famous ridge, Striding Edge, in the Lake District. And Scafell Pike, England's highest mountain, also in the Lake District. The Borrowdale volcanic tuffs were deposited by several explosive eruptions of incandescent volcanic ash similar to the eruption, that destroyed Pompeii in 79 CE. The Silurian, 443 to 419 million years ago. The final collision between Avalonia and Laurentia thrust up the huge Caledonian mountain range, as high as the present-day Himalayas, the roots of which are now the mountains of eastern USA, Scotland and Norway. The heat and pressure resulting from this collision metamorphosed the sedimentary and volcanic rocks originally deposited in the late Precambrian, now exposed as gneiss, schist and slate, and which make up the bulk of the Scottish Highlands, including the Grampian Mountains. Some enormous and complex fold structures developed, which are bounded by faults hundreds of kilometres long, known as the Great Glen Fault and the Highland Boundary Fault. Masses of molten rock were intruded into the base of these mountains, creating the granitic cairngorms, which provided the stone used to build the granite city of Aberdeen. By coincidence, the join between the two continents lies beneath Hadrian's Wall, the traditional border between England and Scotland, but it is deep below the surface, covered by younger rocks. The collision also affected much of Wales, giving us the metamorphic Welsh blue slate. The climate warmed up, causing rising sea levels. Plants such as algae, lichens and mosses were beginning to invade the land. Bees were able to survive on bare rock, as there was no soil. The greening of the land was followed by an invasion of arthropods, animals that include insects, spiders, crustaceans and scorpions, aiming to exploit this new food source. Due to their exoskeletons, they were able to withstand the harsh terrestrial environment, higher gravity, desiccation, and ultraviolet radiation. Fossils of the world's first vascular plants, and therefore the first true land plants, known as Cooksonia, have been found on the Welsh borders. Silurian rocks and landscapes. Flysch formations, commonly found in remnant basins at convergent plate boundaries. These are repeated cycles of upwardly fining sedimentary rocks grading from conglomerate at the base through sand, silt and mudstone. They are formed by repeated underwater landslides or turbidity currents, as the seabed tilted or was disturbed by tectonic forces. The Grampians, Scotland. Remnants of those volcanic island arcs caught up in the closing Iapetus Ocean. The Cairngorms, Scotland, granitic mountains formed in the roots of the Caledonian mountain range, now exposed by erosion. Wenlock Edge, Shropshire. Formed by a massive Silurian coral reef, which is packed with marine fossils such as algae, corals, brachiopods, trilobites, ostracods and crinoids. So now we come to the next major era, the Upper Paleozoic. 419 to 252 million years ago. As you can see, it consists of 3 geological periods. The Devonian, 419 to 359 million years ago, followed by the Carboniferous, which lasted until 299 million years ago, and finally the Permian, which ended 252 million years ago. These rocks make up the central spine of Britain, with older rocks to the northwest and younger rocks to the southeast, with Devonian rocks in the Orkneys and northeast Scotland, and Devonian and Carboniferous rocks in the Scottish Midland Valley. The Pennines and Lake District are composed of mainly Carboniferous rocks, with a narrow band of Permian age along the eastern margin. North and South Wales and the Welsh borders contain more Carboniferous rocks, and Devonian rocks sweep across Mid and South Wales. More Carboniferous rocks are found around Bristol and the Mendips. Devon and Cornwall contain rocks from all 3 periods. Also, large parts of North, Central and Southern Ireland are composed of Carboniferous and Devonian rocks. The Devonian, 419 to 359 years ago. Britain is now located in the arid desert zone, about 10 to 15 degrees south of the equator. The erosion and destruction of the Caledonian Mountains had begun, and thousands of meters of sand and boulders were accumulating in deep sedimentary basins to the north and south, similar to the Ganges Delta today. This created the Old Red Sandstone, which now forms much of southern Scotland and Wales, particularly the Brecon Beacons. It also forms the Great Cliffs of the north coast of Scotland and the Orkneys, notably the Old Man of Hoy. Continued volcanic activity in Scotland formed Ben Nevis. The Devonian period is also known as the Age of Fish, and remarkable fossils have been found in lake sediments in the north of Scotland. Periodic changes in the salinity of the lakes killed huge numbers, and beautifully preserved specimens can be found in the flagstone quarries of Caithness. Ammonites also appeared for the first time. Vascular plants evolved with roots and stems, and branches reaching for the skies to disperse their spores. The first soils were also formed. The first vertebrates also emerged from the sea, as fish fins evolved into limbs and early amphibians colonized the land. Arthropods and insects also continued to diversify. However, this period ended with another mass extinction, actually a series of them, affecting mainly marine life, including trilobites and reef-building corals. 35% of genera and 75% of species were wiped out. Devonian rocks and landscapes. One of the iconic Devonian landscapes is found in the Brecon Beacons in South Wales. Here, there are hundreds of meters of horizontally bedded Old Red Sandstone. These are mainly medium to coarse fluvial deposits derived from the erosion of the Caledonian Mountains to the northwest. Ben Nevis is the remains of a Devonian volcano which exploded and collapsed into a caldera, similar to Krakatoa, in 1883. The Old Man of Hoy is a 150 meters high stack, cut out of the Old Red Sandstone cliffs in the Orkneys. The North Devon coast is another place where you can see Devonian rocks, often steeply tilted or deformed by the later Variscan orogeny. The Carboniferous, 359 to 299 million years ago. Britain continued to drift north and now lay on the equator. To the south, a deep ocean called the Rheic Ocean stretched across Cornwall, Devon and France. As sea levels rose, this tropical ocean spread across Britain. The seas were teeming with life, and the algae, shellfish and coral reefs produced an enormous thickness of Carboniferous limestone, which now forms the hills of the Yorkshire Dales, the Derbyshire Dales, and the Mendips, as well as most of Ireland. Shallowing of this sea produced the coarse-grained millstone grit which gives us the character of the Peak District. As the sea retreated, swamps of dense vegetation gave us the coal measures upon which so much of Britain's prosperity would be based in the far future. Shortly afterwards, an injection of magma into the limestones created the Great Wind Sill, upon which Hadrian's Wall, Bamburgh Castle and Dunstanburgh Castle now stand. At this time, the Midland Valley of Scotland was a less hospitable place. Here there were tropical forests, shark-infested lagoons and numerous volcanoes, the most famous of which is now Edinburgh's Castle Rock, Arthur's Seat and the Salisbury Crags. The atmosphere had its highest ever oxygen levels, 33%, as opposed to today's 21%, which allowed insects to proliferate and grow to enormous sizes. For example, dragonflies with a wingspan of 1 meter. The disappearance of the Rheic Ocean, the Variscan orogeny. Like the Iapetus Ocean 100 million years before, the Rheic Ocean was destined to disappear. As mentioned earlier, the continent of Avalonia had split from Gondwana during the late Silurian period and drifted north to merge with Baltica and eventually collided with Laurentia during the Ordovician. This formed a new continent called Laurussia. During the late Carboniferous, Laurussia and Gondwana collided, pushing up another giant mountain range across much of Europe and southern Britain. This event is known as the Variscan orogeny. By the way, if you studied geology during the 60s or 70s, you may remember this event being called the Hercynian orogeny. With the wider acceptance of the theory of plate tectonics, most academic institutions now favour the title Variscan. The roots of these Variscan mountains are now the varied landscape of Cornwall and Devon. Rocks buried beneath this mountain range were heavily deformed, creating dramatic formations now seen in the cliffs of North Devon and Cornwall, and contact metamorphism created the slates, such as Delabole slate, which is still quarried today. Other deeply buried rocks were melted to form granites which rose upward, eventually to become exposed by millions of years of erosion as the Dartmoor granite and the granites of Bodmin Moor, Land's End and the Scilly Islands. The granite remained hot for millions of years and water circulating through it, and through the surrounding rocks dissolved metals and redeposited them as minerals such as copper and tin in cracks and fissures. The world-famous mining industry of Cornwall therefore owes its origin to this continental collision. Part of the ocean floor somehow refused to sink and got caught up in this monumental rock pile, forming what is known as an ophiolite. This was eventually eroded at the surface, giving us the Lizard Peninsula. The lizard is therefore unique in Britain, being composed of oceanic crust, a rock called serpentine. This was a very complex orogeny spanning almost 100 million years as Gondwana slowly collided with Laurussia. As well as affecting Devon and Cornwall in the UK, the Variscan orogeny also formed mountains from the Iberian Mountains in Spain and Portugal, Brittany and the Massif Central in France, the Black Forest in southern Germany and the Harz Mountains cutting across both Germany and the Czech Republic. The mystery and miracle of coal. As a short interlude, I have two little mysteries for you to think about. Question 1. 90% of the world's coal comes from the Carboniferous period. How can this be? What special circumstance allowed its formation in such large quantities, but only in one limited time period, and then never again? Question 2. Why is coal always found in distinct seams, separated by other rocks? I'll give you a minute to think about answers to these questions, and I've set a 1-minute timer, so get your thinking cap on. Time's up. Now, let's take a look at the answers. I wonder how many you got. I hope you've had a good think. Let's see if you came up with these answers. Question 1. Trees evolved a complex organic polymer called lignin, which is a key component of plant cell walls, particularly in wood and bark, providing rigidity and structural support, as well as protection against pathogens. However, when the trees died, the existing bacteria and fungi were unable to decompose this tough polymer. Enormous quantities of vegetable matter accumulated in coastal swamps, became buried and compressed to eventually form the coal beds that are typical of this period. But in the Permian period, white rot evolved which could break down the lignin, so very little coal has formed since then. Question 2. In the coal measures formation, we often find repeating cycles of shale, silt, sand, seat earth and coal. Different sediments are deposited in different depths of water, shale in the deepest depths, then silt and sand at shallower levels. But what caused these sea level changes? It now appears that with Gondwanaland located at the South Pole, Large ice sheets developed, and a series of glacial periods followed which caused sea levels to fluctuate. That is why coal today is always found in distinct seams separated by repeating sequences of shale, silt, sand and coal. Carboniferous rocks and landscapes. Carboniferous limestone is beautifully displayed at Malham Cove, where chemical weathering has dissolved the rock and formed a huge curved indentation, just like a cove found on the coast. Chemical weathering also formed another striking feature known as a limestone pavement, where water has invaded vertical and horizontal joints in the rock and dissolved it, leaving the impression of huge paving slabs. This one is in Ingleton, in the Yorkshire Dales. Massive granite batholiths formed beneath Devon, Cornwall, and the Scilly Isles during the Variscan orogeny. Although formed at great depth, the surrounding rocks have now eroded away, leaving the granite exposed at the surface, as can be seen in the granite tors of Dartmoor in Devon. The Peak District in Derbyshire is chiefly formed of millstone grit, a coarse-grained sandstone which was once used to make millstones for grinding flour. In some places, such as Kinderscout, it has been eroded to form really weird shapes, such as the woolpacks, seen here. The Carboniferous period is best known for the formation of coal, of which there was plenty in Britain, and was mined extensively to power its industries. The coal measures can be seen as thin black horizontal beds in the terraces of the mine. However, the age of coal is now past, and here we see Fosse Fran, the very last coal mine in Britain, which closed down in November 2023. The Permian. 299 to 252 million years ago. In the Permian period, all the continents of the world were now joined in one huge landmass known as Pangaea. Britain was now north of the equator, about where the Sahara is today, and in the middle of a huge, hot desert. Vast dunes of sand moved across the land, and these have been preserved as the new red sandstone in places such as Dawlish in Devon, Nottingham, Penrith and Dumfries in Scotland. This rock makes a fine building stone, and examples can be seen in many towns and cities. Salt lakes existed in this desert, much like the Dead Sea today. Great thicknesses of salt were laid down, giving us the productive salt mines of present-day Cheshire. Other minerals also crystallized in these lakes, such as anhydrite and, that most useful of minerals, gypsum. Deposits of gypsum are to be found mostly in Nottinghamshire and Staffordshire. Another well-known rock formed in the Permian period is the Magnesian limestone of northeast England. Another innovation was the evolution of amniotic eggs, which allowed reptiles to break the link with water that amphibians depended upon. This allowed reptiles to extend their ranges to drier, more continental environments. At this time, the reptiles were flourishing and had split into two groups, one of which was to give rise to the dinosaurs, sauropsids, and the other to the mammals, synapsids. This period of Earth's history witnessed the most devastating extinction of all. The Permo-Triassic mass extinction around 250 million years ago extinguished 56% of genera and 95% of species, providing the opportunity for the remaining groups of animals to prosper, in particular the reptiles that were to give rise to the dinosaurs. This mass extinction is also known as the Great Dying. The causes of this extinction were many, but seems to be a combination of massive flood basalt eruptions in Siberia, which released both carbon and sulfur dioxides, raising global temperatures, reducing oxygen levels, and acidification of the oceans. Permian rocks and landscapes. Langstone Rock, at the southern end of Dawlish Warren in South Devon, is composed predominantly of Permian desert breccia, deposited as coarse alluvial fan and flash flood debris shed from the rapidly eroding Variscan uplands. Its angular clasts, cemented in a red sandy matrix rich in iron oxide, form the striking cliffs beside the coastal railway, a textbook exposure of Britain's post-Variscan desert sedimentation. It belongs to the Exeter Group New Red Sandstone and represents proximal debris flow deposits rather than classic Aeolian dune sands. The Great Wind Sill is a horizontal layer of dolerite, intruded into the Carboniferous limestone at the very beginning of the Permian. It was formed by crustal extension following the Variscan orogeny and extends about 50 miles across Northumberland and Cumbria. Lindisfarne, Dunstanburgh and Bamburgh castles were all built on it, as was much of Hadrian's Wall. A 300-year-old landmark, the tree at Sycamore Gap, was felled by vandals in 2023. The cliffs at Seaham in County Durham are composed mainly of magnesian limestone, also known as dolomite, dating from the late Permian. They were deposited in the warm, shallow Zechstein Inland Sea, which flooded eastern England after the desert conditions of the early Permian, forming carbonate sediments that later lithified into the pale yellow limestone seen today. Now we come to the Mesozoic era, with periods and rocks that we are probably more familiar with. The Mesozoic, Greek for middle life, lasted from 252 to 66 million years ago and comprised three periods. The Triassic from 252 to 201 million years ago, the Jurassic from 201 to 145 million years ago, and the Cretaceous, which ended 66 million years ago. Triassic rocks are found in Northern Ireland and the Lake District, also in Lancashire, Cheshire, the Midlands and Yorkshire, as well as in South Wales, Avon, Somerset and Devon. Jurassic rocks are found in a wide band sweeping down from North Yorkshire through Oxfordshire and Wiltshire to Dorset. Cretaceous rocks are found in East Yorkshire, Norfolk, the Chiltern Hills, Salisbury Plain to Dorset, and the North and South Downs in Sussex and Kent. The Triassic, 252 to 201 million years ago. Following the Permian mass extinction, also known as the Great Dying, life recovered only gradually. The early Triassic is almost entirely devoid of fossil remains. One of the few reptiles to survive this harsh desert climate was the strange-looking Lystrosaurus, which dominated during the early Triassic. High levels of carbon dioxide led to very high temperatures, and chemical weathering caused rocks to break down. Reptiles evolved into dinosaurs, which went on to dominate during the rest of the Mesozoic era. The first mammals also evolved during the Triassic but remained small, nocturnal, rodent-like creatures. Conifers and ginkgos evolved as they were better able to cope in the arid environment than the tree ferns and lycopods of the Carboniferous and Permian. Britain occupied the latitude where the Sahara Desert is found today, with a climate even harsher than exists there now. By the late Triassic, the Tethys Sea started to form as Laurasia and Gondwana began to separate again. Sadly, the Triassic ended with yet another mass extinction. About 47% of genera and 80% of species were lost. The likely cause was massive volcanic eruptions from what is now known as the Central Atlantic Magmatic Province, which began to form as Pangaea broke up and led to rapid climate change, ocean acidification, and rising carbon dioxide levels. Triassic rocks in landscapes. Ladram Bay in South Devon has cliffs of a red arenaceous rock known as the Otter Sandstone, part of the Sherwood Sandstone Group, which was deposited in a desert environment. It is highly cross-bedded, showing the remnants of sand dunes. This forms one of the main reservoir rocks of the nearby Witch Farm oil field. There have been rare vertebrate fossils found here, particularly the beaked Archaeosaur rhynchosaurus. It is overlain by very fine-grained clays of the Mercia Mudstone Group, again deposited in arid conditions. This acts as the caprock of the oil field. Early Triassic rocks are exposed at the cliffs at St. Bees Head on the coast of Cumbria. These form the St. Bees New Red Sandstone member, which is part of the Sherwood Sandstone Group, and were deposited by a massive, low sinuosity braided river system. The stone is fine-grained and contains sparkling mica, and is still extracted for building restoration. The Mercia mudstone is well exposed in the Aust Cliffs on the southwestern side of the Severn estuary, close to the Severn Bridge. The Cheshire Basin was occupied by an inland sea in the early Triassic, the evaporation of which left a thick formation of halite, also known as rock salt. This has been mined for over 200 years and is still used today for de-icing Britain's roads in the winter. The Jurassic, 201 to 145 million years ago. Britain is now located in subtropical latitudes, similar to the Middle East or the Bahamas today. Sea levels were now rising, which led in the early Jurassic period to all of Britain being submerged, except the Scottish Highlands, East Anglia, and Cornwall. However, sea levels fluctuated over millions of years, providing a great variety of limestones, sandstones, and clays, which were laid down in the shallow tropical seas. All of these rocks contain the fossils of marine creatures like corals, ammonites, and belemnites, but occasionally fossils of land animals are found, such as the dinosaurs of Oxfordshire, where even their footprint trackways have recently been discovered. Dinosaurs diversified into a wide range of forms, including terrestrial, such as Megalosaurus and Cetiosaurus, fossils of both of which have been discovered in Oxfordshire. Marine, for example, ichthyosaurs and plesiosaurs, both of which were famously excavated by Mary Anning near Lyme Regis. Aerial, including pterosaurs, again from Lyme Regis. The discovery of Archaeopteryx fossils in Germany gives evidence of the emergence of the first birds. However, no specimens have been found in Britain. The Atlantic started to open as Pangaea broke up and North America moved away from Africa. Jurassic rocks and landscapes. The Cotswolds are formed of gently dipping Jurassic oolitic limestones, deposited in a warm, shallow sea. Durdle Door formed where waves exploited weaknesses in near-vertical Jurassic limestone at the edge of the Lulworth Cromple, gradually eroding a cave that was enlarged into the natural sea arch seen today. Kimmeridge Bay exposes the dark, organic-rich Kinneridge clay, whose bituminous shales not only supply the small nodding donkey oil well at the clifftop, but also form the principal source rock for much of the oil found beneath the North Sea. The Isle of Portland in Dorset comprises a fine to medium-grained late Jurassic oolitic limestone, eponymously known as Portland stone. Renowned for its strength, durability, and ease of carving, it has been widely used as a building stone, most famously in many of London's historic landmarks, including St Paul's Cathedral. The Cretaceous, 145 to 66 million years ago. Finally, the world looks more recognizable. The Atlantic Ocean widened as first Africa and South America, then Europe and North America drifted apart, completing the breakup of Pangaea. Britain was located about 10 to 15 degrees farther south than its current position, placing it in a warmer, subtropical latitude, roughly equal to southern Spain today. Well-known dinosaurs, including Tyrannosaurus rex, Triceratops and Velociraptors, thrived in the Cretaceous, as did famous British examples such as Iguanodon. Baryonyx. And Pelorosaurus. The Hastings beds and Weald clay of Sussex and the Isle of Wight represented a shallow water environment where the bones of dinosaurs became fossilized in the rocks. The southwest coast of the Isle of Wight is currently one of the best dinosaur collecting sites in Europe. The Cretaceous also saw the arrival of flowering plants. The oldest flowering plant was thought to be Montsechia vidali, a Cretaceous aquatic angiosperm whose fossils were found in the Weald and in Spain. However, in 2018 an even older plant was discovered in China, Nanjinganthus dendrostula, which is thought to date from the Jurassic. But there is still some debate about whether this was a true angiosperm. Nevertheless, there is no argument that modern flowering plants such as magnolias and water lilies first appeared in the Cretaceous. A rise in sea levels in the late Cretaceous to the highest levels since the Ordovician saw widespread flooding of the northern hemisphere, which laid down a great thickness of chalk over much of northern Europe, as can be seen by the green areas on this map. In fact, sea levels were about 170 meters, 560 feet, above what they are today. Over 30 million years, a layer of chalk up to 2,000 meters thick was deposited. But how did such a great thickness of chalk come about? During the late Cretaceous, Britain lay beneath a warm, shallow sea that covered much of northern Europe. Global sea levels were very high, and nearby land was low-lying, so little sand or mud entered the water, leaving it clear and ideal for carbonate deposition. The climate was also unusually stable because Earth was in a greenhouse state, with CO2 levels around 800 to 1500 parts per million, roughly 2 to 4 times higher than today's 420 ppm, largely due to intense volcanic activity and rapid seafloor spreading. With no large polar ice sheets and warm, relatively uniform ocean temperatures, microscopic algae called coccolithophores thrived in huge numbers. When they died, their tiny calcium carbonate plates settled to the seabed and accumulated over millions of years to form the thick chalk deposits seen across southern England today. It is present under most of southern and eastern England, but isolated remnants can be found on the Antrim coast and around the Western Isles of Scotland. The Cretaceous period ended with yet another mass extinction. Only this time it came not from molten rocks below the surface, but from space. Most Earth scientists believe that a massive asteroid, 10 miles wide and weighing about 3 trillion metric tons, hit the Earth at 45,000 miles per hour. The energy released has been calculated to be the equivalent of 100 million Hiroshima-sized bombs, all exploding at once. The point of impact was near what is now Chicxulub on the Yucatan Peninsula. The explosion instantly vaporized everything for hundreds of kilometers around. Within the first minutes, a magnitude 10 to 11 earthquake rippled through the planet. Only tens of minutes later, mega tsunamis up to hundreds of meters tall raced across the Gulf of Mexico, and coastal regions around the Atlantic were flooded hours later. During the first hour, molten rock and ejecta was blasted into space and began falling back, heating the atmosphere globally. The sky essentially became an oven. Massive wildfires ignited worldwide, even thousands of kilometers away. This is when animals not killed by the blast or tsunamis started dying from radiant heat. The skies became dark, and an impact winter set in. Temperatures fell by 20 degrees in most places. Photosynthesis virtually stopped, and very little vegetation grew, starving herbivore dinosaurs, closely followed by the carnivores. In all, 75% of species on land and sea died out, but for one group of animals, extinction was total. Having survived and thrived some 150 million years, the age of dinosaurs was over. Evidence for the Chicxulub impact comes from a thin global layer of sediment at the Cretaceous-Paleogene boundary that is unusually rich in iridium, an element far more common in meteorites than in Earth's crust. The same boundary layer also contains shocked quartz, glass varials, and tsunami deposits, while geophysical surveys beneath Mexico's Yucatan Peninsula reveal a roughly 180-kilometer-wide buried impact crater of exactly the right age. Credit for the initial discovery goes to father and son, Luis and Walter Alvarez, who found an iridium-rich layer of sediment in Italy during the 1970s. Avian dinosaurs are the only ones to survive the mass extinction. Two examples are Asteriornis maastrichtensis and Vegavis ii, which evolved into modern birds. Small mammals also made it through the mass extinction. One example of such is Purgatorius. It is possible that this 15-centimeter-sized animal and its relatives survived because of their nocturnal habitat, small size, mostly lived in underground burrows, and the fact that they were omnivorous helped them overcome the cold temperatures and exploit the small quantities of food still available. These small rodent-like mammals eventually evolved into all the diverse mammal species, including bats, primates, antelopes, and whales. In the sea, many species were hit hard because acidification of the oceans killed off much of the plankton, which formed the basis of their food chains. Arthropods such as horseshoe and retroplumid crabs, as well as a number of species of ostracods, survived, as did many smaller ray-finned fish and deep-water sharks. And coelacanths, originally thought to have died out during the Cretaceous extinction, but were rediscovered by Indian fishermen in 1938. Many amphibians, crocodilia, and freshwater fish such as catfish made it through the extinction as well. The survival of these species can be attributed to the fact they were mostly detritivores or omnivores, or lived in habitats sheltered from the major effects of the asteroid impact. Cretaceous rocks and landscapes. The Chiltern Hills. The Seven Sisters in East Sussex. Nodules of hard flint are often found within the chalk. Thought to have been formed from remains of marine sponges, this was invaluable to early man for the making of tools. The North Wessex Downs, where the mysterious white horse was carved into the chalk around 3,000 years ago. Flamborough Head, Yorkshire. This lies to the north of one of the fastest eroding coastlines in Britain, with over 30 villages and towns having been lost over the last 400 years. Finally, we come to the last era in our journey, the Cenozoic. This began 66 million years ago, and we are still in it. There are three periods in the Cenozoic era. The Paleogene, Greek for ancient born, lasted from 66 to 23 million years ago, followed by the Neogene, newborn in Greek, which ended 2.6 million years ago, and the current period, the Quaternary, which has lasted for the past 2.6 million years. If you studied geology before the late 1980s, you may remember the Tertiary period. The International Commission on Stratigraphy gradually replaced this with the Paleogene and Neogene periods between 1989 and 2008. Cenozoic rocks can be found in East Anglia and the Thames Estuary, as well as the Hampshire Basin. The Cenozoic can also be described as the age of mammals. The Paleogene, 66 to 23 million years ago. In the early Paleogene period, between 63 and 52 million years ago, the last volcanic rocks in Britain were formed. The major eruptions at this time produced the Antrim Plateau, the basaltic columns of the Giant's Causeway, and the lavas and igneous intrusions of the Inner Hebrides of Scotland. As the Tethys Ocean closed 50 to 30 million years ago, the Alpine orogeny formed the Pyrenees, Alps, Atlas, Taurus, Caucasus, Zagros, Hindu Kush, Karakoram, and Himalayan mountains. An early phase of the Alpine orogeny, about 50 million years ago, was responsible for the shaping of the London Basin syncline, the Weald Artois anticline to the south of it, as well as the North Downs, South Downs, Wessex Downs, and the Chiltern Hills. During the period, the North Sea formed and Britain was uplifted. Some of this uplift was along old lines of weakness left from the Caledonian and Variscan orogenies long before. The uplifted areas were then eroded, and further sediments, such as the London clay, were deposited over southern England, while the English Channel was characterised by mudflats and river-deposited sands. Much of the Midlands and north of England may have been covered by Jurassic and Cretaceous deposits at the start of the Paleogene, but these were lost through erosion. By 35 million years ago, the landscape was colonised by trees such as beech, oak, redwood, and palm, along with grasses. Mammals diversified rapidly to fill vacant ecological niches left by the extinction of the dinosaurs. From primitive mouse and weasel-like ancestors, all of today's mammals evolved, including primates, elephants, whales, monkeys, rhinos, rats, cats, and bats. The Neogene. 23 to 2.6 million years ago, the climate of Britain cooled and became drier throughout the Neogene. The Antarctic ice sheet started to form about 20 million years ago. North and South America joined, causing a change in ocean currents that may have contributed to the onset of the later Pleistocene Ice Age. As Africa continued to move north, southern Europe emerged out of the shrinking Tethys Ocean as a series of islands, until all that was left of this once vast ocean were the Mediterranean, the Black Sea, and the Caspian Sea. Britain was still connected to Europe, allowing easy access to fauna and flora from the south. In Britain, temperate forest and grasslands formed, promoting the evolution of herbivores. Primates, which had first emerged during the early Paleogene, also evolved and diversified. Hominids split from chimpanzees about 6 million years ago, and the genus Homo developed about 4 million years later, but you will have to wait until the next period, the Quaternary, before Homo sapiens shows up. The Quaternary period, 2.6 million years ago until the present day, composed of two epochs, Pleistocene, 2.6 million to 12,000 years ago, also known as the Ice Age, Holocene, the last 12,000 years. However, it may be that we have entered a new epoch, the Anthropocene, but there is much debate about when that actually started. I'll talk about that a bit later. This graph shows temperature fluctuations over the past 542 million years. Note that there are different timescales along the horizontal axis. The graph shows that it has been much hotter in the past, and that there have been very stable temperatures for most of the last 12,000 years, until the sudden increase since the Industrial Revolution. The Earth can cope with temperature changes, however climate zones will shift, and sea levels will change. The real question is, can we cope with these rapid changes? Our civilizations are based on systems of agriculture that are fixed geographically, and 33% of the world's population lives within 100 meters of current sea level. The Pleistocene, 2.6 million to 12,000 years ago. The Pleistocene Ice Age. The Pleistocene was not just one long period of glaciation. There were at least 5 glacial periods: Baventian and Beestonian, Anglian, Wolstonian, and Devensian, with intervening interglacial periods. In fact, as the diagram shows, the interglacial between the Beestonian and the Anglian was very long, over 400,000 years. The interglacial periods were perhaps 1 to 2 degrees warmer than today, and fossils of animals we normally associate with North and Sub-Saharan Africa, such as hippopotami, lions, elephants, hyenas and rhinoceroses, have been found in southern Britain, some dating back over 600,000 years. The fact that Britain was still joined to Europe and via intermittent land bridges to Africa and the Middle East facilitated their migration, and it is likely they moved back and forth between glacial events. Despite being the shortest glacial period at 54,000 years, The Anglian glacial had the greatest extent, reaching as far south as a line roughly between Bristol and London. It was this ice sheet which diverted the River Thames from its former northerly course to roughly that which it follows today. Lasting some 244,000 years, the Woolstonian glacial was the longest. The ice sheets reached several kilometers in thickness and transformed the British landscape, eroding deep U-shaped valleys, leaving side valleys with smaller glaciers as hanging valleys. The ridges between the valleys were also worn back, creating sharp ridges called arêtes and bowls called corries. Terminal and lateral moraines were deposited at the ends and sides of the valleys, and the eroded rocks were dumped as glacial till, sometimes damming streams to create temporary lakes. As the ice sheets retreated and then advanced again, glacial till and moraines would have been reworked. Much of Britain's glacial landscape that we see today was formed by erosion during the last glacial event, the Devonian, since most of the glacial carving caused by the Anglian ice sheets was smoothed out by the succeeding interglacials. Although it didn't extend as far south as the Anglian, it left behind the landscapes of Scotland, Wales, Yorkshire and the Pennines. To the south of the ice sheets there would have been barren tundra with only the hardiest plants and animals able to survive. The animals which dwelt within the frozen landscapes of the Ice Age adapted to their environment. Many were large and developed woolly coats, such as mammoths and woolly rhinoceroses, brown and polar bears, giant deer and reindeer, and predators such as saber-toothed cats, cave lions, wolves and hyenas. Due to their generally larger size than modern equivalents, they are collectively known as megafauna. Early hominids also lived in Britain. The earliest known is an example of Homo heidelbergensis, dating back some 480,000 years, which was found at Boxgrove in Sussex and henceforward eponymously called Boxgrove Man. Homo sapiens evolved only 200,000 years ago, although the earliest British example, found in Devon in 1927, dates back some 44,000 years. The Holocene. The Holocene epoch, 11,700 years ago to the present day, although there's a bit of controversy about that, which I'll talk about later. Evidence of rapid warming following a final Pleistocene cold period known as the Younger Dryas was found in ice cores recovered during the North Greenland Ice Core project between 1996 and 2003. This established the formal start of the Holocene epoch as 11,700 years ago relative to the year 2000. The warming was so rapid that temperatures rose between 5 and 7 degrees Celsius in a matter of decades. Isostatic equilibrium was re-established as northern Britain was relieved of the weight of the Devonian ice sheet, which caused the northern half of the country to rise and the south to subside. Coastal processes intensified, with erosion, sediment transport and the formation of dunes, salt marshes and barrier beaches becoming dominant geological agents. During this video, we have mentioned a land bridge connecting Britain to Europe several times. Over the last 90 years, evidence has been gathered from artifacts recovered by fishing vessels, seismic surveys and core samples from the drilling for hydrocarbons in the southern North Sea, which shows it was actually a large fertile area which has been named Doggerland. The findings show Doggerland was a region of hills and valleys. The upland region of Dogger Bank, for instance, was formed from a massive heap of moraine rock, pummeled, pushed and dumped by moving ice sheets. As the earth grew warmer, the ice sheets retreated and meltwater rivers carved valleys through the uplands. Trees and other plants quickly colonized, and there would have been many lakes, wetlands and marshy deltas, rich in life. These highly productive coastal habitats would have been very attractive to hunter-gatherers, who exploited the abundance of fish, fowl and mammals. Remains of mammoths, rhinos, hyenas and other creatures now extinct in northern Europe are common, but most likely died out due to climate change rather than overhunting. Meltwater from the retreat of the glaciers and the warming of the proglacial tundra caused the formation of the modern river systems. Tundra was replaced by birch and pine woodlands, and later mixed deciduous forests of oak, elm and hazel. In the uplands, peat formed. Whilst the land bridges still existed, large mammals such as red deer, orch, and wild boar repopulated Britain, as did hunter-gatherer humans. The sea levels rose, completing the development of the English Channel and the flooding of Doggerland. Britain thus separated completely from Europe about 6,000 years ago, and finally became the island we know today. Eventually, the climate of Britain stabilized to that found today. Neolithic farming developed about 6,000 years ago, as well as monument buildings such as Avebury and Stonehenge, and tumuli to mark burial sites. An agricultural landscape began to form during the Bronze and Iron Ages, which was further developed by medieval land clearances and the later onset of field enclosures, giving rise to the characteristic patchwork nature of the British countryside. The onset of the Industrial Revolution led to the growth of urbanization, whilst mining and quarrying became more intensive, resulting in large deposits of waste as spoil heaps. These had an effect on sedimentation, and burning of fossil fuels began to influence the atmosphere. Human activity increasingly influenced geology through deforestation, farming, drainage, and mining, accelerating erosion and modifying soils, rivers, and wetlands. Canals became a feature of the landscape, shortly followed by railways, whilst roads were constructed everywhere. Slowly, the natural landscape disappeared until nowhere was devoid of evidence of human intervention. Cenozoic rocks and landscapes. Stair Hole in Dorset is a small cove where intense folding and faulting have exposed steeply tilted Jurassic and Cretaceous strata, dramatically illustrating the deformation produced by the alpine orogeny. The Giant's Causeway formed about 60 million years ago during the Paleogene, when extensive volcanic eruptions associated with the opening of the North Atlantic spread thick basaltic lava across Northern Ireland. As the lava cooled and contracted, it fractured into the distinctive hexagonal columnar joints, creating the remarkable pavement of interlocking basalt pillars seen today. The Black Cullens on the Isle of Skye. Paleogene volcanics. What we're looking at is not really a mountain range at all, but the solidified magma chambers beneath an ancient volcano, later carved into spectacular ridges by Ice Age glaciers. The rocks here are primarily gabbro, along with peridotite, alavolite, and basalt, giving them their characteristic dark, jagged appearance. The cliffs at Alum Bay in the Isle of Wight expose a spectacular sequence of Paleogene sands, clays and gravels deposited in rivers, lakes and coastal environments about 65 to 50 million years ago, as southern Britain lay in a warm subtropical climate. During the following alpine orogeny, these sediments were compressed and tilted almost vertically, producing the famous multicolored strata seen beside the chalk stacks of the Needles. There is one last chapter that could be added to our story: the dawn of a new epoch, the Anthropocene. Increasing human influence is now detectable in the geological record through sediment, geochemistry, and climate signals. This has led to a proposal for a new epoch following the Holocene. However, the proposal was formally rejected as such in 2024 by the International Commission on Stratigraphy and the International Union of Geological Sciences, suggesting it should be treated as a Holocene event instead. Regardless of this, Martin and Phil both believe that the human impact on the Earth's climate, and ultimately, the rock record, is great enough that it should be included in our story of the geology of Britain. So there we are. We have completed our 3 billion-year geological journey from the oldest Precambrian rocks, the Lewisian gneiss, to the most recent rocks deposited during the last Pleistocene Ice Age. It's been a long and sometimes tortuous journey, but I hope that this has given you some insight into the geological history of the UK. Here is a short recap of how the British Isles have been assembled, like a massive jigsaw puzzle, over the past 3 billion years. Igneous rocks. Precambrian. Lower Paleozoic. Upper Paleozoic. Mesozoic. And finally, Cenozoic. Voila! The jigsaw map of Britain is complete. So, our geological map of Britain is complete. But does this geology have any effect on the look and feel of our landscape? What do you think? Can you see any similarities? Let's look at a few examples. The hard, mainly metamorphic and igneous Precambrian rocks can clearly be seen in the mountains of the Scottish Highlands. The grey waxen slates of the Lower Paleozoic gives us the Welsh mountains. The Carboniferous limestone and millstone grit form the backbone of our island, the Pennines. The softer Triassic rocks have been eroded to form the lowlands in Cheshire and East Yorkshire. The Jurassic limestone has formed the Cotswolds, whilst its clays have produced the Vale of Oxford. The Cretaceous chalk can clearly be seen in the Chiltern Hills, as well as the North, South and Wessex Downs. And finally, you can also see the granite moors in Devon and Cornwall, Dartmoor, Bodmin Moor and Land's End. We hope that we have given you some insight into the long and complicated geological history of the British Isles, without confusing you too much. We've been on a long and sometimes circuitous journey, both in time and space, starting more than 3 billion years ago. Together, we've travelled back 540 million years in time and almost 10,000 miles in distance to get from where we started, close to the South Pole in a Precambrian, to where we are now, 50 degrees north of the equator. We've endured 3 major orogenies, lots of volcanic eruptions, 5 mass extinctions and at least 4 major ice ages. Our country has been assembled piece by piece, worn away, raised up again, and eventually formed to its present shape. In some cases, life even formed the very rocks on which we stand, literally in our case, as here in High Wycombe we're on chalk, which as you now know is made up of the shells of trillions of microscopic phytoplankton. The wandering of Britain. Finally, let's have a look at what was happening to the Earth on a global scale, as the continents moved, collided, and split apart again. I've placed markers to show where Britain and Scotland were at various points in time. See if you can spot other major events, such as the Caledonian mountain building, and where India collided with Asia to form the Himalayas. What an amazing story. And what a shame that more people don't realize how we got here, or even give it a second thought. Thank you for watching, and goodbye.